Okay, so see, this figures tells us that different color gamuts for different applications. For examples, think about this one, this rectangle, the dotted rectangle. So this color gamut is used primarily for color monitor, and you see for the color monitor, so we'll have to choose these 3 points, right? So this point is from red area, and this points from the green area, and this points from blue area. So roughly this is the case, but depending on the monitor and the company and the quality, this might be adjusted, but this is roughly a typical color monitor color gamut. Okay, gamut mean a particular color space area. But think about the movie and the film, they need more colors, right, compared to the monitor that we perceive. So that's the reason why you see this color gamut basically used for film. And think about this is whole the possible color space. So whatever color gamut we chose, definitely it should be confined within this color space, but producing this entire color is impossible. So it's basically theoretical. So this is hard to produce these entire things, and costly even. So this is the chose. This is the some typical things. And how about the printing, inks that we use for printing purposes, the color that is color space that we use, basically this one is that one. So this is how they may have some different properties that when it printed on a paper. So based on that, they chose that kind of colors. Okay. Now see, let's say some specific, color monitor specifications, or it's a simply, spec, color spec, right, for monitor. You know, for examples, the NTSC system. The NTSC is, it simply means, National Television Standard Committee or something. It's basically North American, television system. So for that, they use, this is the red point they use. Definitely, this red, it means on the chromaticity diagram, what is the, red point. So this is this XR and YR. Similarly, these, pair of values, they determines that which, green spot we use on the chromaticity diagram. So this is that roughly we say green color. And similarly, this is the blue points, and blue point is specified by this pair of points on the XY chromaticity diagram. And similarly, this is the white point that we use, as we explained before. And more or less similar. So if you look at the color portion here, so let's we just enlarge this a little bit. So for example, the NTSC system that we are talking about, the red is roughly see this is XR, basically 6.7. So it's something like maybe around this place, right? So around this place mean I would say that this one. And how about the Y? Y is 0.33. So 0.33 means maybe let's say this one. So this point is basically for NTSC. So this is the XR YR, or we can say this point is used as a from the red portion. And how about the green one? Is 0.21 and 0.71. So 0.21 means let's say in this area, and 0.71 it means something like here, right? So green area roughly maybe this is the green point. And how about the blue point? The blue point is 0.14 and 0.08. So that means maybe 0.08, maybe roughly here, right? So this is the point. So color gamut for NTSC television systems is basically this one. Okay, so this triangle that I drew. And how about the white point? White point is 0.31 and 0.31. So it's roughly, because see 0.31 is here, so maybe we can say this is 0.31, 0.31. And similarly, other, for example, this is another, standard systems that is perhaps, for, motion pictures. And this is European Broadcast Union. So accordingly, they select different based on their needs and based on their perception. So this is the thing. So how about, let's think that so definitely, there are so many colors, right? Let's say we have this color gamut for our particular applications, but how about, but this theoretical somehow, let's say, how we can represent this color, which color, how it is out of this color gamut. We don't have capacity to produce that one, but if somehow, for other things, for other object, this color comes in, then how do we approximate that one? So this is very easy. Let's say this is a white point for our color gamut, and and these colors that that's coming from a particular object and somewhere. So what we do is we just draw a straight line between these 2 points, and then we see that which point is intersect on the color gamut line. Okay, for example, this point. So that means this color will be approximated by this color, because this is the closest color of this color, right? So because this is the closest color of this color, so when these sorts of color comes in, so we can assume that this is the color. So similarly, other colors also can have. For example, if somehow this colors comes in, you see this is originally within the color space, the possible color space, but this is not within our own color gamut that we are interested in or that we are working with. So what we do, we just draw a straight line, and then you see what is this color. So exactly these colors, so that means this color will be approximated by this one. So this is the idea, what we mean by an out of gamut color. It says out of gamut color approximation, okay, by an in gamut one. Okay, so this is somehow you need to understand it. And now other things that it is good to say is so which one? So maybe this one. Okay, so this one, you see that we had a relationship from earlier slides, that z is basically 1 minus xy. When we discussed x, y color space, you just go back and check the mathematical equation. So here you see we must choose the x and y in such a way so that z negative, doesn't become negative. Okay, so we cannot take the negative values of any of our these normalized values. Okay, and in fact you can see that from for example here you see that if you see these 2 values, is basically this xr is basically 1 1, right? So z, you will not find that if you x and y, you will not find negative. So if you find a negative one, so that means there is some problem, and that problem will affect our mathematical or approximation or image algorithm. Okay, so ultimately we reach to a point that where we now can analyze the color in a more detail. So definitely the de facto standard is RGB and primarily used for monitors. And you can remember this diagram. Actually, this is a very cool diagram, very useful diagram. You can use it in many situations. So this diagram means roughly you can think about like that. Let's say someone is just like spreading in its hand, and spreading his hand. So in this hand it is basically red, and in this hand this is basically green, and this one is blue. Okay, so just to remember some sort of, so this is red, this is green, and this is blue. And in between red and green we have yellow, and in between this red and red and green, yellow and red and blue, we have this magenta color, and then in between blue and green we have this cyan color. So this RGB is a color space, a color model. Similarly, this MY is also a color model. That things. Okay, so from this diagram you can basically draw some sorts of conclusion. You can remember some fact. So for example, if you mix this red, green and blue, definitely this white will be coming. This is one of the things. Now other things is very interesting is, see, this cyan and you see this red, basically they are facing to each other in some sense. Let's say that they are far away, so they basically attract each other. And this is the case. Attraction means just to remember the things. So that means this cyan color basically absorb this red color. Okay, but see, cyan is basically is more close to this blue and green color. So cyan color reflects this blue and green color. It doesn't absorb. So similarly, this magenta color, it absorbs this green color, but it reflects red and blue color. In the same argument, this yellow color reflect blue color, whereas it absorbs it absorbs blue color, but it reflects magenta and cyan color. So sorry, I just mess up. So this yellow color basically absorbs blue color, and it reflects red and green color. So the same way we have to remember this magenta color. Magenta color, it basically absorbs green color and reflect red and blue color. Okay, so this is the idea. So that means this magenta, yellow, cyan and RGB, they are basically subtractive to each other. Okay, if one is additive, another is subtractive. So this is how this works. Actually, this cyan, magenta, yellow, this is a color model, and this is basically a subtractive color model primarily used for printing purposes. For examples, if your dye color is then cyan, it absorbs red color and reflects blue and green color. That I explained. And if your dye color is black, so it means it absorbs all of the color and it reflects none of them. So ultimately, based on this concept, we can even think that how we can convert between RGB color to CMY color or CMY color to RGB color. To think about that one, so let's say we think about a color box or color cube. So in this cube, you see this is an axis. So this is called red axis. Let's say I go here. So okay, here it is. So see, so actually this is the same one that I'm using. So here, so I'm not sure, maybe the blue. So you see, so this is the cube box, and let's say this axis is basically red axis, and this one is green axis, and this one is your blue axis. Okay, now this red, green, blue, you can think of that, let's say this is the starting point, definitely. So this point is basically this is a start from 0, and if you go up to this point, it's become 1. And similarly, if you go to the green, so this at this point it is 0, and at this point it is 1. We are thinking like a equal cube. And if for the blue axis, if this is 0 and if this is the 1, so the minimum is 0, the maximum 1. So maximum 1 mean is roughly 255 level, and minimum is 0. So either way, you can think of this number, or you can think just simply 0 to 1. Okay, from 0 to 1. So at this point, then at this point it is basically 0, 0, 0. So that means it's a black point, black color. But how about at this point? So at this point, you see that red axis is definitely 1, and the green is 1, and the blue is also 1. So this is basically white point. So this diagonally situated these 2 points. This is a perfectly black point, and this is perfectly white point, and all other color point inside this cube. Okay, so for examples, maybe this is on particular color, this is on particular color, this is on particular color, and particular color, whatever it is. Now how about if we replace this axis with something like how to say that, let's say red, if we replace this one with the other color model, that is yellow and cyan and magenta axis, then how? Same thing, that if we replace this red, green, blue with yellow, cyan, magenta, then what we have is, then let's say this exactly this point, or that I'm explaining from here. So this point is for the, let's say this is the cyan axis, and this is the yellow axis, and let's say this is the magenta axis. So similarly, this is 0, and at this point 1, this is 0 at this point 1, this is 0 at this point 1. Okay, so if it is so this point is exactly, this point is 0 0 0. So that means absence of, that means cyan is 0, yellow is 0, magenta is 0, and that means we have the perfectly white point. And if we mix up all of this color is, with the maximum proportion, so that means at this point you have the cyan is 1, the magenta is 1, and the yellow is 1, and then you come up with a black. Because if you remember, what is the model? So model is, if dicolor is black, it absorbs basically all the colors, or if you mix all the colors, the color become black. So there it is. So it is exactly, if you keep the side by side, it is exactly the opposite. It is exactly opposite. This one is exactly opposite to this one. Or in another word, maybe it's here, or in another word, if you have let's say C, M, let's say if you have R, G, and B values, and you like to convert to cyan, magenta, and yellow color, so you see the relationship is basically, if this one is 0, so that means here this become 1, and if this one is 1, so this one becomes 0. So it is exactly opposite. So how can do so? So that means if we, let's say we have a if we subtract 1, R values from 1, so this is basically become cyan. Similarly, if we just subtract green value from 1, so it become like this sorts of magenta. Similarly, if we subtract B from 1, then it becomes yellow. This is exactly the same, right? So you see, when it comes to blue, this is blue. It's exactly opposite of this one. This is red, so this is exactly cyan. This is green, and this is magenta. Just the relationship is just 1 minus something. So in a matrix notation, you can just keep it as a matrix notation. Let's say this one is a one matrix notation. So that means this is the case. Then how we can represent? This is exactly, see, CMY equal to 1 1 1 minus RGB. Or similarly, if we just have CMY, so we can convert from CMY to RGBs in this way. That's RGB equal 1 1 1 minus CMY. So it is very simple. Now how about the conversion between, actually it is possible to convert any color to any color. Okay. Now one good model is, whatever color you have, you just convert to RGB color, and then from RGB color you just convert to another color. So similarly, let's say if we have XYZ color space, you know what is XYZ color space, and let's say you have RGB color space, how to convert that. So let's say we have the RGB values like this in a matrix form that we are taking. Okay, so this is RGB. That means you can basically transfer these colors by multiplying with the transformation matrix, and then you have the XYZ color. Okay, so what is the transformation matrix? That need to be determined. But somebody already calculated and done the experiment, and they show that this transformation matrix is somehow this one. That means 0.3935 and something like this, 3 by 3 matrix. Okay, so that means if you just multiply this RGB with this transformation matrix, then you have basically this XYZ values. So, and definitely the X values, if you see this, if you do the multiplication, this X value is basically, you see, you just take the R value and multiply with the 0.3935, and then you take the green value and then you multiply it with the 0.3653, and then you take the blue value and then you multiply to 0.196, and then you sum up these numbers, then you have X. Similarly, we can find out the Y value and the Z value. Okay, so this is how we convert from RGB to XYZ. So and if you do the inverse things, inverse if you take the inverse matrix of this one and then you multiply with this XYZ, you get the RGB. So this way you can basically transfer from one to another. Now here in this values that we use, so this is basically the real values of RGB, right? For example, let's say R. Definitely this R value might be from 0 to 255. This is one way to think of. Or you can also consider let's say from scale 0 to 1. Okay, so in this case 255 means 1. You have to remember that. So fraction also is basically used in many books or in many methods or system specification. Okay, and now let's say we know that this is the R value, but do you remember that gamma correction? Sometimes we use gamma corrected values or gamma correction. We do that. So to do that, we need to supply additional information, or for example, so you have an image, right? This is, let's say, 3x3 image. Okay, this is a 3x3 image, and let's say this value is somehow, I don't know, and let's say this is red plane. Okay, this is red plane somehow. This is a color image that have 3 plane, and I'm talking about this red plane. And let's say this value is 110, this value is maybe 120, this value is 3, this value is maybe 0, this value is 1110, this value is 1112, this is 37, 55, and 59. So these are some gray level for this red plane. Okay, now we know that if we just transmit this one through a electronic device, and so that we can see on the monitor, this value will be changed, and that is called gamma characteristics of the electronic device, right? So what we do is we know that this value will be changed. Let's say we have this let's say we are talking about this very fast pixel. We know this 1110 will be converted to something like maybe 120. Okay, we know that. So that's what we do is we don't store this value in our memory space or hard disk drive. When we store this image, when we save this image, what we do is let's say so we don't store 1110, rather we store, let's say 99. Okay, because we know that if we transfer 99 through electronic devices, maybe that value will be 1110. Let's say we know these things. Okay, 1110. So we don't the original value is 1110. Original value is 1110, but we know that when it goes to the monitor, it will be changed to 120. But this is not the exact value that we want. Rather, what we do, we can do some experiment and then we can see. So we can rather store another value, let's say 99, and that we know that 99 value will be converted to 1110 when it display. So these 99 values that we are talking about now, this 99 is called gamma corrected value. Gamma, you see this gamma corrected value. Gamma corrected value of what? This 1110. We know the 1110 is the original value, but its gamma corrected value is 99. So in many image storage mechanism, we basically handle with these gamma corrected values, not these original image values. So interestingly, if this R means let's say a R value, its gamma corrected value in many where we represent by R prime. So similarly, so this transformation when we did from RGB to XYZ, this R value, this RGB value is basically our original R value. But if we use gamma corrected value, let's say not RGB values, rather we use R dash, G dash, B dash values, at the time this transformation matrix coefficient need to be slightly adjusted, and we can show that this becomes like this one. So this means if this R is basically so you see this is, we have a correction, this should be R dash, G dash, B dash, R dash, G dash, B dash, R dash, G dash, B dash. Okay, so that means if we have the gamma corrected values, so at that time we slightly change this coefficient and we use this equation. Now let's talk about ACE's V color model or color space. ACE's V color model is basically based on polar coordinates, not Cartesian coordinates. And then ACE means hue. it means color family. It represents, let's say red, it distinguishes between, one color to another color, from red to yellow, from green to blue. So that hue means that. And saturation means this is the color sensitivity, that how color intensity, how is strong or weak, or how much color, what is the amount of color that we can perceive. And the value is basically the luminance information or brightness information, that how dark or how light a color is. Now to think is a more intuitive pattern, and let's say this one. So this cylindrical disc, we can think that when we think about ASV color, that is hue, saturation, and value color model. So hue is basically, if you just rotate this cylinder, then you see different color is coming. So think about that one cross sectional of these things, like this color wheel. Let's say this color wheel. Now if you move this if you move around this wheel, or let's say wheel itself is rotating, so that means let's say we start from here at 0 degree, and then you move in this place. So at 0 degree, maybe this is red color, and then you go, for example, here at 60 degree, it is basically yellow color. So this is called color family. So when for 0 means let's say red, and 60 degree means yellow, and cyan means 180 degree, and then if you say that ACE is let's say 270 degree, so it means this is basically violet color. So this is what it is. This hue value basically determines the which color family it is. So also think about this one. This is also some scale for age, that as you move up and down, you basically choosing different colors, basic scales. Now how about the saturation? Now think about that you are basically, let's say at the at the very this point, and then you just move to the outward. So that means across this wheel. If you go along this radius, then what you see at the center is basically it seems that there is almost no color perception. But as you go to the outwards, you can see that the amount of color, it seems more and more. So that means saturation of red color itself is increasing, right? So that means wherever you set, let's say you set in this position, and you can set this in amount of saturation determines the AS values. So that's what it means. So the saturation means as you go along the radius towards the outwards, so your saturation values increases. So AS values definitely it start from 0, and let's say it's ended with 1. So how much saturation you have? So this means 0%, and 1 means 100% saturation. 100% saturation means there is a perfectly red. And then you have something called the value. The value means actually how much light you are exposing onto that color space. So this is basically the brightness information, that it is basically in the dark mode, or it is basically in the very white color mode. So depending on this bright level, the color perceptions also sometimes keep changing, right? So as you see that our age can take any value between 0 degree to 360 degree, or we can say from 0 to let's say 1, if you convert to this entire scale to 0 to 1. The saturation might take any values from 0 to 1, or maybe 0% to 100%. And the value also it can take from 0 to 1 or 0% to 100%, the way you want, right? Now how about the conversion between RGB to ASSV, or from ASSV to RGB? So here I'm showing that RGB to ASSV. So this is pretty much someone calculated for us. We are computer scientists, we don't need this, just we will use this equation. Okay, so see there are how you determine the ACE, the hue from RGB. Let's say you have given an RGB, how you can. So there are 4 expressions that you can use. That for example, let's say you have an RGB value and you see that which one is the maximum. If the R value is the maximum, then use this expression. If green is maximum, use this expression, and if the blue is the maximum one, then use expression. And if you see that there are two maximum, the minimum is same, so that means all are same. So at that time the hue is 0. That means it started from 0. Okay. And the saturation calculation is very easier. If the maximum color is 0, that means in RGB. So why this is starting this one? So better I stop this one, right? Okay. Squid. Oh, okay. So sorry for the disturbance. Now you see that if the maximum is 0, then we say saturation is 0. Okay. And if the maximum is not 0, that means if other values, then we can use this expression. And the value is just the maximum one is the value. That means it is always the case, in fact, that if you have R, Z and B, which is the maximum, let's say R is the maximum, so that gives you the most intensity, most brightness, contribution. Okay, now let's take an example, so it will be good. So it is very simple. Let's say we have this RGB color and we like to convert to ASUS color. So the very first one, you see that red is the maximum, because if red is the maximum, then we use this expression, right? This one. So if you use this equation, this is 60 degree multiplied by, you see, this one is green minus blue. So that means 100 minus 50, and then divided by max minus mean. So max is 255 and the mean is 50. And then mod 360 degree. Okay. The mod, what is mod? So mod is just, for example, let's say you have 17 and you are creating, okay, what is the 17 mod, maybe 5. It means you just divide this one. So divide, maybe, after divide, you see that 5 multiplied by 3 is 15, and then you have 2 remaining, right? So this 2 is the result. So this is called mod operation. That things. Okay, so this is what it is. So you just come up with, so you just simplify this one, then you see 15 mod 360. So if you divide, definitely the remainder is 15. So the hue is 15 degree. Okay, so hue or H is basically 15 degree. So 15 degree means you just go here. So somewhat maybe this is, maybe 15 degree mean maybe this is at this point you are. And how about the saturation? Now saturation is definitely maximum is not 0, so you will use this expression, that is 1 minus mean by max. Now 1 minus mean by max, that is mean is 50 and max is 255, so 1 minus 0.196, and if you just calculate it, so subtract it, so it becomes 0.804. So that means roughly 80% saturation. Now roughly 80% saturation means perhaps maybe you are here. Okay, and then you have the V, that is value is the maximum in 255. So that means value is perfectly bright information. So value is this one. This is the maximum one. So this is how we convert this one. Now how about from ASUS V to RGB? You can try it yourself. Okay, now then we have this color information, that is called YUV model. So this color model was originally used for pale analog video. So this one, the pale, it means phase, alternate line or something. So pale analog video, but then later on it's also started for using digital video. So this color model is basically very simple. So in this color model, you see this is called YUV, and interestingly the Y is the same as our original XYZ model. Okay, so YUV, so this Y is the same, and that what is this Y, and it just we saw that from our earlier conversion here. that when we saw the XYZ conversion here, you see that this Y was basically, like this one, that 0.299R plus 0.587G plus 0.114B, right? So this is the one that we are actually using here. You see, the Y is the same as, and by the way, this Y, we are writing in terms of, the XYZ, this Y, because we are saying this Y is the same as from XYZ model. And the Y in XYZ model can be represented, in terms of RGB is like this one, that, 0.299R plus 0.587G plus 0.114B. Definitely this is basically, as this is, gamma corrected one. So definitely, this R, this G, this B, this R, G, B, this all should be gamma corrected values. Anyway, so Y, that means luminance information is the same. The only difference is now that how we construct this U and V. And this U basically, it's also very simple, that you just choose one, this, you just subtract this B, this, you just subtract this Y value from this B value, and the V you determine something like, you just you take this one and then you just do this operation. Okay, so that means you subtract this Y value, that means that is Y, this gamma corrected Y value, from this gamma corrected blue value, and the same way then you have U, and then you do the same, you subtract the gamma corrected Y value from gamma corrected red values, and then you have the V. And if you do so that means you just do this one, and then so this one is, you just replace the value. For example, you just replace B dash, so that means blue dash, and then you just replace these values. Okay, you just replace this one, that is B blue dash minus subtraction, and what you will have is then U basically becomes B dash minus Y dash, and let's say I just write here, then you will have something like this, minus 0.299 R dash minus 0.587 green dash, and plus 0.886 B dash. Okay, so this will be your value for U. Similarly, you have a value for V, that is if you just subtract this one, that is R dash minus Y dash, you just replace this Y dash here, and then you just simplify, and after you simplify, then what you will have is 0.701 R dash minus 0.587 green dash, and then minus 0.114 B dash, something like this. Okay, so that means what, you now have the Y, and you also have now U is this one, and then V is this one. Now if you represent this is a matrix form, let's say Y dash U V in this matrix notation, then what you have, a transformation matrix, and you have then R dash, G dash, and B dash, right? So ultimately we are converting this YI view and RGB, from RGB to YUV, that's we are converting. Then you need a transformation matrix, and the transformation matrix we already calculated. Yeah, so the calculation comes here. You see the Y dash is the same as this one, 0.29 R, this value, so this is exactly this one, this coefficient, and this RGB, and the EU is basically this one. You see the 0.29587, 0.886, so this is this one, and this is the V. Okay, so ultimately this is the transformation matrix that we just constructed just by manipulating and by just algebraic manipulations of this one. So ultimately what is this? This is basically, you see, this is subtraction. That means from a reference point you are just subtracting these values from a reference color. Okay, so this is what we are saying, that this is a difference between a color and a reference white. Okay, so this is the reference color, is basically a reference white color that represented by this B dash R dash. And To do so, there are some advantages, perhaps in video processing or something, presentation, those kind of things. So then, it is good that what we understand this transformation, but these values that we get, u equal b dash minus y dash, and v equal r dash minus y dash. It's okay, but when we implement these things, there are some computational issue and something. Okay, so to better understand and to better manipulate that one, we can when we do the implementation, we basically rescale these differences. Okay, scaling doesn't change the property of a color basically. So you just do the scaling. So you just multiply this one by something like 0.49, and you just multiply this one something like 0.87, and exactly this one. The u is basically this one, and the v is basically this one. The same, the same b dash minus u, you just scaled up, scale down, and this is also you are scaling down. And then if you do so, then definitely then you just again you do this algebra that we showed here. If you do so, then definitely this transformation coefficient will be slightly changed, and that change actually been reflected here. So if you have any RGB color, then you can go back to YUV color, and then in this case you just use this transformation matrix. Definitely this RGB basically is all our the gamma corrected values here, and also you do the reverse, that's vice versa. You have the YUV color, then you go back to RGB color. In this case, definitely you need inverse one. So this is the inverse one of this one. Okay, so this is what you do, and then you have YUV color, and this YUV color we exactly use for digital video. Now think about it. If you just really see the YUV color, how it looks like. Okay, so let's say we have the U axis in this direction and the V axis in this direction, and the U value basically from minus 0.5 to plus 0.5, and the V also from minus 5 to minus 0.5 to plus 0.5, and then you thus have this two-dimensional space and the Cartesian space, and then you can perceive the where is this color is actually, right? You see this is the red area, this is the purple area, this is maybe the blue area, this is somehow the green area, right? So this is how it comes. Well, perhaps later on we will see the digital version of this YIV is actually called YCBCR model. Perhaps we will see these things later on. Then you have YIQ color model. Okay, there are lots of color model, and the reason is each color model is good for a specific purpose. Some color model is good for image processing. For example, ASSV, we saw ASSV that is good for image processing algorithm development, and some color are good for monitor purposes, for example RGB, and some color are good for printing purposes, for example CYM or something, that color model, and some color model good for broadcasting. For example, this YIQ model is good for television broadcasting. So what is YIQ? YIQ, as you see, the Y is the same. Its difference is now YIQ. Basically, this IQ is the color space, and Y is the luminous information. The luminous information is mostly same. Okay, so IQ is basically also nothing new. It is just a coordinate change. You think about this one, this color space, this YIV color space, but it turns out that if we just move this, if we just rotate this color space by 33 degree, and you introduce the new axis, for example, if you just rotate this one, and this maybe, let's say you come up like this kind of things, let's say this is the one, this is called in phase component, or let's say I axis, and similarly it's 90 degrees, let's say Q axis. So this I and Q basically the rotated version of YIV color space. Okay, so and this rotation basically done by 33 degree rotation more appropriately. So what is this one, R dash 0.49 to 1 R dash. This is exactly the UV that is stuff that we saw, right? This one, and this 0.87 this one, right? So if you see this, exactly this term that I'm saying, and this is exactly this term saying, right? So this is somehow that we said that UV stuff, right? If you remember that, yeah, this is that UV. Now what we do is basically we just manipulate, by sine, cosine, and then we just come up with, just new axis, that is, I and Q. And if you forgot that how to transform this one, this is, I have a very small, things for you, just for your reference. Let's say we have this old axis, let's say small x and small y, and we like to convert to a new axis, let's say, capital X and capital Y. Now how we can do this transformation? So this transformation, if you transform the x to this x, you basically do these kind of things. That how much you move, let's say by theta degree, so your x will be x cos theta plus y sin theta, and this y coordinate will be minus x sin theta and y cos theta. Okay, so the same things we did here. So you see, cos theta, sin theta, cos theta. Sin and cos is always coming to us, right? Now, after you do so, then you just simplify this one. Okay, if you just simplify this one, this I would be something like maybe 0.59 r dash minus 0.27 g dash minus 0.32 b dash, something like that. And this q will be something like, q would be 0.21 r dash minus 0.52 g dash and plus 0.31 b dash, something. Okay, and definitely our y is the same as we had from the before. So if you just take it's a matrix matrix representation like this one. If you just do this matrix representation, so this one is 1, and then if you just so take this r z b here, then for the r you have this line of coefficient for this RGB, and for the next line you have this coefficient, and the very first one is your I coefficient. This is exactly the same one, you see this one, right? So that means you just put these RGB values and apply this transformation matrix. If you multiply, so then you come up with YIQ is color model and color space. Now one aspects of this YIQ space, we can show that it basically saves some bandwidth when you do the communications, and that's why we use this color model for TV broadcasting, because in television broadcasting the transformation of video signals, it takes lots of color image, color frame. So from each frame it can save some sort of frequency. So by looking, this is this one. Okay, so again it's see the I basically now from -1 to +1, and Q is also from -1 to +1, and I basically is the orange blue direction. Okay, the I is basically from orange to blue direction, and the Q is basically purple green direction, so that means this direction. So if you keep it side by side, it looks like this one. This is UAV, and this is somehow this is YUV, and this is YIQ color model. So this is there are different sorts of color model. We end up here. So I hope that you understood our color stuff. And now I will show you some demonstration, okay, in Python, that how we can convert from one color to different colors. So here we have see the multimedia lab with Python 2, and this is about color conversion, right? So in color conversion, let's just do a few conversion that we learn. So the first one is, let's say we have RGB image and how we can convert to gray level image, and or HSV model, or we can convert to YUV color space. Okay, so the very first things is see this one that will be first reading the image, as you know that we have Lena image, and to read this image, we are using this scikit image, right? SK image, and we will be using its IO and color module, that kind of stuffs. So that's why we just call this. So the very first one is very straightforward. These things, that you can read this image, Lena image, and with this Lena variable, and if you just show, if you run these things by clicking here, then you have this one, right? that this image, Lena image, you know that. Now let's we convert this is an RGB image, so let's we convert that to a color image, and for that we are using this color sub package of SK image package. So that's why we write from SK image import IO and also color sub package. Now first we read the image and then captured Lena, and then we pass this Lena variable into this function color dot within this color sub package there is RGB to gray function. Then if you do it, so it will be converted to RGB image. Now then let's say we keep this RGB converted gray level image to Lena underscore gray in this variable, and this object if you pass and if you show try to show it that io.image show, then if you run these things, then what you have is this one. Okay, so this is the gray level image, and exactly you understand that this was our Lena color image, and now this one is our grayscale image. Now how about converting to ACSV color space? We took the same image, the Lena image, and then we pass to this function, that's RGB to ACSV image, and pretty much anything just I followed the same setup and same coding style, and then if you run it, then you see this is our ACSV color space. But definitely when you convert an RGB image to ACSV image, so some information is lost because of the conversion of float stub. And then let's say we have again the same image, Lena image, we read, and then we can convert to YUV space. So just there is RGB to YUV function, and then you pass the Lena image, and then if you just show image and you just run it, then you have these sorts of image. Yeah. So again, it looks like slightly different version, but this is possible when you go to one color space to another. The conversion that the display will not be original, some losses will be there, and also sometimes some numbers are clipped away some data. Okay, so this is YUV space, that's what we have. Now let's say even a gray image you can convert to an RGB image. So how does that work? The gray image basically a single plane that is in two-dimensional array. For example, we had the cameraman image, if you remember that inside the scikit image there is some data, and from the data you can actually read some built-in image. For example, the cameraman image is basically one built-in image, and that cameraman image we read, and let's say this variable name is mycam. Now within this mycam, if you show these things, if you run it, then if you show like io.image show, then this is basically the simple gray level image, and this is exactly two-dimensional 512 by 512 image. So if you forgot that shape, if you just run the shape, you see 512 by 512. Now this one plain image we can convert to an RGB image, but definitely it will not be a color image, by the way. But if you just call this gray.rgb, before we had RGB to gray, now if you just have, there is another function called gray.rgb within this color sub package, then it will be converted to an RGB data. Now RGB data, the other two plane, just it will be copied, the same data will be copied in three plane. Okay, now if you show it, you see it is the same image basically, because all the values in every plane, that is in red plane, green plane, and the blue plane is the same. That's why it is the same image we are seeing. And if you see this dimension, this mycam.color, these dimensions, because this is converted gray level image converted RGB image from gray level image. If you see the dimension it shows that 512 by 512, and it has three plane, and each plane contains the same numbers. You can check it. So that's why by looking, it's the same. But we can do some tinting on grayscale image. I mean, it is still a gray level image, but you can label some red portion, yellow portion, depending on the manipulation of some plane. Okay, for example, we have three plane here, the R plane and green plane and blue plane. So let's say we change the red plane number. we keep all rows, all columns, but just we are changing this, red plane, the very first plane. And let's say we change this number, by multiplying 2. That means all the numbers in the first plane, now after we convert it to an RGB plane, just we double the number, okay? But other plane, for example, the green plane and the blue planes remain the same. And if you do so, then if you just, take this my image now, if you just run it, then you would see this kind of image. It's still the same gray level image, but it has now RGB image, and this RGB, reflects some sort of, tinting. That means we have changed one plane, and that's why we see, and we changed, onto the red plane. That's why some, red, portion we are seeing here. Similarly, if you do, let's say you do, changes on the green plane, that means the same things. And now you can see there is some green, changing happening over here. Now this tinting can be, made as something a little bit more, fancy. Just let's say we need a, matplot library pyplot package, and we just, import the same data package data color. Also, we also import image as float, sub package. So that means we will have an image, and we'll convert that image as a float number, okay? Because the float is, you can have longer, and also the decimal values, those things. And then, the same as we just, read the data camera image and, do this kind of stuffs. You just multiply, red multiplier is this one, yellow multiplier this one, you do subplotting, and then, you do these kinds of things. And just what I need, you can understand this coding, but what I need to say is, if you multiply the green and blue channel by 0 and leaves only the red channel, that means you just eliminate, green plane and blue plane, just you keep the red channel, okay? So that means the bright red image will be showing. Similarly, if you just make the blue channel 0 and other red and green channels intact, so it will, because the red and green mixing will be yellow, so you can form the yellow shading of that kind of image, right? So if you run it, then you see the first one is reddish version, and the second one is yellow version. Because here in the first image, what we in this image, what we have done, we have made all the green and blue plane 0. That's why it looks like reddish. And here the same cameraman image, here we have made all the blue plane pixel 0, and we have kept as it is the red and green channels, and the green and red basically mixing, it produces some yellow impression. So this is some demonstration that what I had for you. So see you in the next week.